Chapter 7, we're going to conclude today's activities with a roadmap that has synthesis in it, making bonds to new bonds from carbon to carbon, that's synthesis. We're going to do it again over here, more synthesis. And we got some new stuff. I'll tell you all the new reactions. There's a lot of them. I'll go new question mark here because you're going to see, we kind of saw that one. All the other stuff's from either from this morning or chapter 4. And where do you even start? Start here. Okay. Molecule is called acetylene. It bothers me, so I have to bring it up because acetylene is usually reserved for this very important unit in biochemistry. It's one of the most common prefixes is acet. Acetyl group normally. Acetylene doesn't have it, does it? It's not a mistake that they named it like this. It's just, it's got historical reasons that they learned later were a mistake. Kind of like I was talking about when they came up with the word aromatic compounds. I mean, to you, if you had never taken organic chemistry, you say, oh yeah, those are the chemicals that smell, right? Well, they were wrong about that. It's aromatic in organic chemistry is molecules with a benzene type ring in them. And the stability of the benzene is what gives them the aromaticity, and it often gives them smell, but they found thousands of molecules that are aromatic that don't smell. So the smell wasn't really the criteria, but they've named them already. There's no acetyl in this. I do see an acetyl later. That's an acetyl there. And that kind of reaction is why triple bonds got their name with acet in it, the acetylene. You can make it into a molecule that has an acetyl in it. It's sort of like son of acetyl, you know? Son of acetyl makes sense? Like bin acetyl? Does that work for you? Or if you're Scottish, it would be McAcetyl, like McDonald's is son of Donald. It's named after it's a relative. It's not named after itself, right? So you see where I'm getting? I don't like it because when I see acet, I want to see a carbonyl with a CH3 because everything in biochemistry's got that, and it bothers me. There's a whole page in the textbook devoted by why it bothers the teacher so much. It says, who came up with the cockamamie idea of calling this thing acetyl? That's in the title. Okay. All right, I'm going on a little too much. Clearly, we're talking about some kind of a, why do you think I gave a pKeq? What am I trying to hint at here? What kind of reactions do we give pKeqs for? Acid-base. You know the pKa of acetylene. What is it? It's a terminal alkyne, so what is it? 25. What must the pKa of, let's see, that acetylene becomes that. This is not even labeled with its partner, but it has to become an acid with a pKa of 35. How did I know that? That is magic. That's the only number that works with the information here. How do you figure out pKeq if you have the two pKa? The one on the left, which is 25, minus X, the one on the right, equals -10. It's right in the middle. The only number that works is the 35. There's only one acid with a pKa of 35. What is it? H2. So I need the conjugate base of H2 in the box. In the box to the left, this is the acid. You can write KH, or if I did this, I just want the H minus, right? I just want to be consistent. I always get rid of the spectator, right? So I'm just going to put a big fat H minus in there. That's the only base that would work to give that result. And you made your loop new for your synthesis. Keep reminding you. Your loop new. It's going to attack something to give us this new group. New group. Can I remind you how you got new groups on before? We put an ethyl group on by having ethyl attached to chloride. There's the ethyl group. We put an S2 pentyl group, 1, 2, 3, 4, 5 group on by starting with R2 pentyl bromide. Yeah, I don't need a fancy, I think the ethyl was a good example. Because in this one, I want an isobutyl. So what are you going to put in the box? Just isobutyl? Try that. You won't get anything. Draw this in the box. You won't get anything. Because you don't have a reaction. No reaction at all. Do you remember what the nucleophile attacked and why? Hey, the mechanism's right here. The nucleophile, lubnu, is attacking a carbon that's positive because it has a halogen on it. Can you fix the answer now? What are you going to attach to this and where? The leaving group. You like BL, BR? BL made up leaving group doesn't exist. BR or CL is where I was going. You see that. BR, CL, I. Those are the three you should always think of. BR, CL, I. Berkeley. There's two Berkeleys in this country, two famous Berkeleys. You know them? Berkeley, like a place? There's a college in California, and there's a most famous musical school in Massachusetts. Oh, yeah. Spelled different. All E's with that one. Okay. So there, you got it. You got your synthesis going to the top. Let's go left and right for our new reactions. What do you have to do if you want to make a ketone? Because that's what this is, right? Versus over here, what's this functional group over here? That's not a ketone, right? What is it? What is it? Right there. Aldehyde. So when I put these things on notes ever, please don't take them lightly. Organic chemistry, especially synthetic organic chemistry, is about interconverting functional groups. So we've learned how to make a terminal alkyne. That's why I'm going to write terminal alkyne. Why is it called terminal? It's at the end. Later, we're going to see an internal alkyne. They're coming up. There'll be one right here. So what you've learned is how to make a terminal alkyne into an aldehyde if you learn what chemicals go in this box. So I would start pieces of paper happening, review pieces of paper. Every functional group is a story. So when we study aldehydes by themselves, you need to know reactions that made them and reactions that they undergo. Always looking ahead. Let's get a page going for aldehyde. This will be your first entry. How do I make an aldehyde? You say, okay, I can start with a terminal alkyne, and whatever chemicals he says here, I'm going to put there, and that'll make me an aldehyde. And then you're going to start another page for ketones and say, oh, I can make those from terminal alkynes with these chemicals. All right. So what chemicals? You don't know. But I'll tell you how to put a boron on the end. Here's some weird stuff. Sia equals sec isoamyl. Sia, you see it there? Sia. Amyl equals pentyl. Amyl equals pentyl. It's old school. So draw me Sia. Here's the chain. How do you draw a sec group ever? Methyl branched immediately, right? Then the rest. Okay. How do you say iso? V at the end. This has both, doesn't it? And it has 5 carbons. That there's Sia. Sia. It's a new group. And if you want to figure out why we have to use HB Sia 2 this time instead of like BH3, which we did in chapter 6, it's called hydroboration. Step 1 is called hydroboration. Step 2 is oxidation. And the chemicals are identical for that one. I don't expect you to remember. We just learned it. But it's hydroxide and hydrogen peroxide. You vaguely remember that one? In the mechanism for oxidation, there were 6 steps. First and last were acid base. Boron alternated between negative and 0 and negative and 0. Negative and 0, remember that? Or 0, negative, 0, negative, 0. And there was making O minuses, attacking borons. There's a lot of pointers I had for 6 steps. And on Monday, you'll see there's a 7th step this time because the intermediate at the end has an alcohol attached to an alkene. So you're going to read about that on the weekend. Read about enols, where ene is attached to OH, and how they undergo tautomerization. There's a lot you have to read on the weekend, I know. And videos and all. I finally have videos, thanks to somebody in this room. Okay. Yeah, we got a lot to do. We always have a lot to do. Never ends. So now you know how to make an aldehyde from a terminal alkyne. That magical list of chemicals. How do you make a ketone from the same terminal alkyne? You're putting the O in the other carbon. You're going Markovnikov. Isn't the O on the more electronegative carbon? More substituted carbon is what I should have said. Isn't this the more substituted carbon and this the less substituted carbon? Yeah, that was an anti-Markovnikov. You're not surprised to see boron involved in that one, are you? No. This one, mercury. Sound familiar? Not mercury acetate this time. Doesn't work as well as this. That means mercury 2 sulfate with water. Don't forget the water. It's everywhere there. And H2SO4. When you're studying, you want to read about oxymercuration / this time they don't call it demercuration because you're using a proton in sulfuric acid to get rid of the mercury. They like calling it this, and it's a great name. Nice. Protonolysis says you use a proton, in this case from sulfuric acid, to cut the mercury off. What part of the words means cut? Lysis is cutting. It's a good word for all of science, not just chemistry or biology. They use it more in biology than chemistry, by the way. Okay. So you're going to read about those. On Monday, we do both those mechanisms. They're big mechanisms are coming up. You're going to have a mercury mechanism on your test. It'll be either the alkene version or the alkyne version. And you'll have the hydroboration oxidation mechanism. It will be the other one. So if I use an alkyne for the oxymercuration on your test, it'll be an alkene for the hydroboration. If I use alkyne with the oxymercuration, it'll be an alkene with the hydroboration. But you're going to have both. Okay, so 2 mechanisms you definitely want to really be solid on. The 2 mercury ones and the two hydroboration oxidation ones. Okay? They're big points. The mercury one's like 11 points, and the oxymercuration is like 13, 14 points. Let's say oxymercuration. Meant hydroboration. The one with boron's worth more. Monday. Okay, I got a problem here. It's not a terrible problem. There's a small typo on your page. I need you to fix this arrow to start up here and then go this way. Okay? So this molecule is reacting with these two things. Is that clear? That box is really not bothering me. There's your box. And I got my strategic eraser out. Make sure you know these things. Yeah, there you go. There's the way to go. That's a big reaction arrow. Here's the end of a box. There you go. Now it's clear, right? So I've got a, what's the KNH2 going to do? Remember that. When you see that molecule, always think about it becoming NH3, pKa 40. So it's acting like a what? NH2 minus. Picking up a proton. So it's an acid or a base. Which one? It's accepting a proton. NH2 minus is accepting a proton and becoming NH3. It's a base. Acids give protons. Bases take. It's taking a proton from the big black thing above the arrow. This thing. What's the lowest pKa? Don't give me this one, this one, this one, or this one. Those are all 50. That one. What is it? 25. So step one, that comes off and becomes a C minus lubnu. C minus lubnu. Copy the molecule. There you go. And that C minus lubnu does a synthesis to the carbon that has a halogen on it in step 2. Which carbon has a halogen on it in step 2? What carbon number? Carbon 2 of what chain? 2-bromo-butane. 4 carbons. Partial credit for this answer. That's carbon 2, right? Of butane, right? You get half credit. How are you going to get full credit? Well, I don't need side products. I don't need for credit ever. But you brought it up, so I'm doing exactly what I said. Students like to see side products, and I often forget to give the side products. It's an organic chemist mindset. We got to go with it. You're still losing. You're going to lose 0.75 points. No, it's a full point. The R. We need it to be S. Because what happens during an SN2 reaction? Your lubnu is going to attack carbon 2 of R2-bromobutane and flip it from R to S. Isn't that what happens during the backside attack? Did I say SN2 by mistake? Yeah, I said it by mistake. SN2 is backside attack. It's the chapter 9 words. Okay, and we're not going to really get there. So if I slip and say SN2, you just think backside attack, and you got it. You got 100%.
So the same thing is the BB?
Yeah, the lube, there's no BB going on here. The BB was in step 1, acid base. Bronsted stuff, step 1.
Okay.
Step 2, the lubnu attacks the carbon with a bromine. You're not attacking an H.
Oh.
So ELA here. ELA. And I need it to be S, so you put your H on there. 1, 2, 3. It better be a wedge because that makes it S. There you go. There you go. And if you're like me, you don't like drawing much stuff over and over again, right? So here's a tip. If my computer ever catches up with us here. Here's a tip that could save you time on tests. You've already used it in like part 2 of last test, didn't you? So I never have to draw those groups again because they're not going to change in these next reactions. Just give this one a different name. I like R prime. R and R prime, you like it? Now H2 and PT is going to do this. Each pi bond gets 2 H's, syn. How many pi bonds in an alkyne? 2 pi bonds, 2 pi bonds. So 2 reactions, right? And then you have to do R and R prime. So that's H2 with the platinum catalyst. Now, if you change that catalyst to this catalyst, it's a combination of 3 chemicals called Lindlar's catalyst, circled in pink. H2 is not circled, it is a reagent. Okay, I want to do this net reaction next because they both have H2. With Lindlar's catalyst, the alkyne will react and make an alkene, and the reaction then stops. Because this piece, lead 2 sulfate, makes the catalyst less active. It's like a volume knob, turning down the volume on the catalyst. All right? Attenuation, we call that. That's what lead sulfate does. That's the catalyst, and this is a poison, they call it, and that's chalk. Seriously, it's chalk. White powdered chalk with palladium embedded on it with a machine. Crush some chalk, get some finely divided palladium. You take a rod of palladium in a file, and you go like this. You want like dust. And then you pound the dust into the chalk. So there's your palladium and your calcium carbonate. They want a lot of surface area. That's why they use the chalk. And then they add the lead sulfate in there and they pound that on there too. All right? So it's a solid. And then you have H2 bubbling through the reaction. And the alkyne reacts, but the alkene doesn't. In this one, the alkyne reacted first to make an alkene, and then the alkene reacts under the same conditions of chapter 6, which are these conditions, to make an alkane. Isn't this an alkane? Alkane. I forgot to put this in the morning lecture. Sentence. These are the most valuable things today. Oh, go ahead. Do my dollar sign backwards. Slightly, this was like a $double. Yeah. This thing's like a $double. So we're adding value, aren't we? Except if you use H2 and PT. You get fired for doing reactions like this, is what I'm trying to say. You're fired. You took a valuable molecule and made it useless. It's an alkane. Alkanes you can't do much with. So, do you remember if H2PT is a syn or an anti-addition? You have the picture of the platinum metal. I drew about 100 platinums in a row. I put a couple H's on top. It was syn because it's like coming from a surface, right? You got to go either on this side from the bottom, or the surface comes from the top. Syn from the top or syn from the bottom. Never one on the top and one on the bottom, or the surface can't be up there and down there. No. So you're going to get a syn addition over here with 2 new H's. Very valuable. You got a double bond with geometry. Was R on the left before? I reversed them, I'm sorry. Double bond with geometry is valuable. That's what the $triple means. And I want you to know right away that the BH3 with acetic acid gives the exact same result. You don't have to draw it. Same as H2 Lindlar reaction. Okay? So we have two ways of making cis alkenes. But that, hey, get a sheet going for cis alkenes. How do you make them? From this kind of alkyne. What kind of alkyne was that? We have to put these in our brain. It's not on the end. Not on the end. If it was, you'd call it terminal. What do you call it when it's in the middle? Internal alkyne. So if you're asked, how can you make a cis alkene? You say, take an internal alkyne and react it with H2 and Lindlar's catalyst, which is this combination. Or take an internal alkyne and react it with BH3 and acetic acid. That's what that is. That's acetic acid down there. So you have to be able to make cis alkenes and trans. That's the last thing we got to do. It's the last box. This is not your normal sodium here. I want to get rid of that blue dot. I don't think I can. I don't know how it got there. I got rid of the Na. White out. Okay. When I have sodium like that, that should be shocking. Shocking. Do you know how much sodium exists on this planet that looks like this one right here?
0.
0. Yeah. 0. 10 billion years ago, all the sodium became sodium +1 because there was a better place for that electron, right? Many other atoms prefer having that extra valence electron than sodium does, right? So billions of years ago, sodium gave up its electron. So when you find sodium in nature, it's always Na+, right? So where are you going to get some Na with no plus, like pure sodium metal? Well, some dude in a lab takes a bunch of salt, he puts it in an airtight chamber with no moisture in there, okay? He runs electricity through it, lots of electricity, a whole ton of electricity. And it reduces +1 to 0. He isolates it and then he hides it in some mineral oil. Why does he have to use mineral oil? Because that doesn't let air in. Sodium metal will react with air. Air, just air, okay? Like Mama Silver, Grandma Silver turns black. Sodium does that in seconds, okay? All right, so you buy that, you buy some ammonia, and you put them together, and the coolest thing happens. When you put the sodium in the ammonia, it's beautiful. Sky blue, like her top right there. It's pretty blue. Yeah, so it's a cool color. The electrons in the ammonia, they get trapped in there and create a complex that they call it a charge transfer complex. There's a lot going on. It's blue. Sodium and ammonia, and what do we get? We talk about this and the new H's. One's up, one's down. That means the R's are one's down, one's up. And these are the cis alkenes. Cis alkene. So similarly here, cis alkene, right? And this is a trans. So you know ways of making cis alkenes and trans alkenes. You know how to make aldehydes. You know how to make ketones. We got a good little starting arsenal of reactions to make functional groups. We're just beginning our study of this. It's going to grow and grow and grow for 2 courses now. Okay? And I think we're done with what we need to do today.